Okay, so this is just going to be our first application of integration. So you guys have probably known for a while how to find the mean of a finite number of values. So when I say the mean, I mean the arithmetic mean, which is if you have a finite number of values and you want their mean, so let's say I do x1 plus x2 plus x3, and I would go up to xn, then I would just divide by n, the number of values that there were. Is everybody familiar with that formula? So we colloquially call that the average. All right, so same idea. If I could do it for y values, and I would compute the average y value of a function if I had a finite number of y values. The problem is any continuous function has how many points along it, even if it's on a closed interval like this? It's infinitely dense, right? There's infinitely many points. So if I want to find the average y value of a continuous function, how do I take the average of infinitely many points? Well, it exists, and we can probably all intuit that it exists, right? So if the low today, let's talk about temperature. Temperature is continuous, right? So if the low today is, a nice cool day today, it's 63 and the high is 79, there's infinitely many temperatures between those two, right? But do you all agree we could probably find an average value for the temperature today? It's somewhere between 79 and 63. All right, so there is an intuitive way to find the average value of a function. Let's come up with the calculus to do this. All right, so if I think of subdividing an interval, hold on one second, let's say this. If I want to find the average value of a function, I'm going to call it f average. Really bothers me, our book, or the book that I use as like the skeleton for this class, abbreviates average as AVE, which seems insane to me. It's AVG, right? We can all agree. So if I want to find the average y value or f value of a function, I'm going to add f of x1 plus f of x2 plus f of x3 and so on up to f of xn, right? And then I'm going to divide by n. All right, so let's look at this in terms of, let's say I have an arbitrary function between a and b. Here's A. Here's B. And let's say I subdivide said function into n subintervals. So I'm actually not doing a finite number of subintervals here. So that when I label these, this is x0 and b is xn, right? And in between I would have x1, x2, and so on and so forth. Something that we've been doing, we're familiar with this. Well, if I'm looking at a finite number of subintervals, I can still find the average y value just by adding up all the y values and dividing by how many subintervals I have. But eventually I'm going to want to do infinitely many subintervals. So I'm going to use some formulas that we already know. A formula that involves n and the length of the interval is the delta x formula, remember? Delta x equals b minus a divided by n. So to find the width of any given subinterval, delta x, I take the width of the whole interval, b minus a, and I divide by n, the number of subintervals that I'm using. Well, I can use that to resolve for n. So if I multiply both sides by n and I divide by delta x, that actually tells me that n equals b minus a over delta x, right? Well, let's go back into my f average formula there, and let's replace the n with its equivalent. So I have x1, f of x1 plus f of x2. Keep adding until we get to f of xn. And now I'm replacing n with b minus a over n. All right, but when I divide something by a fraction, I can simplify that by flipping the denominator and multiplying, right? Yeah. Oh, over delta x, I'm sorry. Thank you. Yeah. Not over n. b minus a over delta x. All right, so if I flip this and multiply, then what I have is f of x1 plus f of x2, and so on, plus f of xn. And now I'm flipping the denominator and multiplying. So I'm going to have times delta x, but divided by b minus a. Okay, so b minus a will be some constant. So I'll factor that out to just be 1 over b minus a. And then a more concise way of representing this sum, isn't that just sigma f of xi from I equals 1 to n delta x? All right, so sigma from I equals 1 to n of f of xi delta x. All right. So there's how I find the average y value of a function over a finite interval, or a finite number of subdivisions, I should say. But how many actual y values did we say there are on a continuous function? There's infinitely many. So what I actually want to look at is what happens as I let n approach infinity. So I'll say if I take the limit then as I let n go to infinity of 1 over b minus a sigma I equals 1 to n of f of xi dx or delta x. Well, this should look like a pretty familiar limit. That's the definition of the integral between a and b. It's just we have one constant multiple that we've added out front, the 1 over b minus a. So this equals 1 over b minus a times the integral from a to b of f of x dx. And that's how you find the average value of a function. So we started with our intuitive definition of how to just find the average of a finite value of y values, finite number of y values, and then we just took the limit as that number approached infinity, and we ended up with 1 over b minus a times the integral from a to b. Yes. Yes, I'm sorry. Not my best infinity I've ever. All right, and you don't need to be able to rederive that. Just wanted to go through it once, but you do need to memorize that formula, which is here's how to find the average y value of a function on a closed interval. Look at that. It's so weird to look at. It's a Canadian author. So like one intuitive way to think about this is what does the integral tell you about the graph? So if this is my function f, what does the integral get me? The area underneath, right? It gets me this. So what we're doing is we're taking this area, we divide out the length of the interval, and it leaves us with the average height. So that if I were to graph in that average height, like here, I would end up with a rectangle that has the exact same area within it as the area under the curve. Does that make sense? All right. Let's do it. Find the average value of a function f of x equals 1 plus x squared on the integral, on the interval -1 to 2. I want to sketch this one out. One plus x squared is just a parabola that's shifted up 1, right? So it's going to have a vertex right there at 1. And at -1, let's see, my y value is going to be 2. And at 2, my y value is going to be 5. Didn't make this graph tall enough. It's like way up here. All right, so this curve on that interval is going to look something like this. Too much coffee this morning. I'm very shaky. All right. So the average y value, any guesses as where you think it is just based on the visual? You had to guess what the average y value is on that interval. 3? Like here-ish? Pretty good guess. Let's see. I'll say f average equals, it's 1 over b minus a, so it's going to be 1 over 2 minus -1 times the integral from -1 to 2 of the function 1 plus x squared dx. All right, so we got 1/3 integral -1 to 2 of 1 plus x squared dx. All right, so let's do the antiderivative now of 1. Antiderivative of 1 is just going to be x, right? Antiderivative of x squared is going to be x cubed over 3. We want to evaluate that from -1 to 2. Yeah, this is complex enough that I think I want to use my calculator. All right. So my antiderivative was x plus x cubed over 3. I'm going to do this clear. 1/3 times y1 of 2 minus y1 of 1, or no, of -1. Where y1 has my antiderivative inside of it. And we get 2. So a little below where the conjecture was, but right idea. Y equals 2 is the average value of the function on that interval. So meaning, here's the area under the curve on that interval in green. If I make a rectangle at y equals 2 on that interval, that rectangle contains the exact same area as the green area. Questions? Okay, so there's one more theorem, and this is the MVTI, the mean value theorem for integrals. And it says, if a function is continuous from a to b, then there exists a number c on that interval such that f of c, which is the average value of the function, f of c will equal the average value of the function, meaning whatever the average value of the function, there has to be a location on the interval where the function attains that average, okay? If the average temperature today is 70 degrees, it must have been 70 degrees at some point during the day because our function is continuous. We couldn't have jumped from 69 degrees to 71 degrees without having touched 70 degrees. Does that make sense? So that's all it says, is that whatever the average value of the function is, if it's a continuous function, then that function must have attained its average value at some point. The other way to think of it is exactly how I've been explaining it geometrically, because you can just multiply the b minus a to the other side, and then you get the integral itself equals the average value times the length of the interval. Well, this is just base times height, right? That's the area of a rectangle. So basically, if there is, whatever the area under the curve on that interval is, there's a rectangle that covers the same area. Okay? And that's just an illustration of that idea. Well, let's do an example where we use some of that information. So let f be the function f of x equals x cubed minus 6x squared plus p, where p is an arbitrary constant. It says find the value of p such that the average value over the interval -1 to 2 is 1. Okay, well, we know the formula for f average is 1 over b minus a times the integral from a to b of the function, right? All right, so for us, what's the average value that we want in this case? It's 1, right? They tell us that we want the average value to be 1. What's the interval? So what's 1 over b minus a? So 1/3. Integral -1 to 2 of our function, which is x cubed minus 6x squared plus p dx. All right, let's just continue to work our way through. Let's take antiderivatives here. Antiderivative of x cubed. 1/4 x to the 4th. Antiderivative of -6x squared. -2x cubed, I believe. You are correct. Antiderivative of p. Careful, P is a constant, right? So Px. And then I'm going to go from -1 to 2. All right. This is actually a calculator problem. I forgot to, here, hold on, I'll do it for you. I forgot to put the oh so subtle tiny calculator in the corner to remind us. So they're going to expect you to use your calculator. This is an algebra problem that would probably be pretty difficult to solve by hand. Let's see, maybe it won't. But we're going to plug in 2 for all the x's, right? And then we're going to plug in 1 for all the x's, or -1 for all the x's. And then we're going to subtract. So this is going to give me 1 equals 1/3 times the quantity. What's 2 to the 4th? Divided by 4 is 4. What's 2 to the 3rd? Times -2 is -16 plus 2px, or 2p, sorry. So that's, I plugged in the top limit. Now I'm going to plug in the lower limit minus, I'm going to put this in parentheses. Plug in -1, I get just 1/4, right? And then this is going to be plus 2, because -1 cubed is still -2, or -1. And then minus p. I mean, I guess this isn't too bad to solve by hand. We're trying to solve for p here, right? So if I were putting this in my calculator, I would put 2 equations. I would put the left-hand side in y1, and then I would put just this entire right-hand side in y2, but replace p with x. And then it's going to give you 2 graphs, and wherever they intersect is going to be your solution, right? But looking at this, I don't think it's that bad. So if I want to get rid of the 1/3, I'll just multiply by 3, right? Now I got 3 equals, I don't know, 4 minus 16 is -12. You see, here's what's annoying, right? What's 2 plus 1/4? 2 1/4? 9/4? Okay. So I get -12, I get minus 9/4. I get plus 3p, right? Yeah, it's not that bad. All right, so then that becomes add the 12, so we get 15 equals -9/4 plus 3p. All right, let's get a comp. 15 times 4 is 60. So 60/4 equals -9/4 plus 3p. So add 9/4, we get 69/4 equals 3p. Divide by 3, p is 69/12. All right, so just a little bit of algebra and arithmetic there. But not too bad. Like I said, that was a calculator problem, so you could have done all these little additions in your subtractions in your calculator and not in our head. All right, last one. Let's put this in the context of position, velocity, and acceleration. So it's been a little while. You remember the relationship between those three, right? How do we get from position to velocity? Derivative, and velocity to acceleration. And so now we know to go in the reverse direction will be antiderivatives, right? AKA integrals. So here they give us a particle moves along the x-axis, so its velocity at time t between 0 and 5 is given by v of t. At time 2, the position of the particle is x of 2 equals 0. Find the average velocity of the particle over the interval z 0 to 5. This is actually superfluous information for this part of the problem. I just pulled this from an FRQ. We don't need that the position at time 2 is 0 here. We would only need that if we're trying to find the total distance it traveled. But remember this, the average value of a function is 1 over b minus a times the integral of that function dx, right? So if I want the average velocity, the average, it's going to be 1 over b minus a times the integral of velocity, I guess that'll be over time, dt, from a to b. Okay, and I'm gonna add an extra onto this, which is at what time I'll say z did v of t equal the average. So I also want to know when. I said did and then just wrote AD. I also want to know when it attains its average velocity. All right. So here all we have to do is plug in the values we have. So the interval is from 1 to 5, or 0 to 5, sorry. That's going to be 1/5 integral 0 to 5 of three times t minus 1 times t minus 3 dt. All right, again, give you a hint that this is a calculator problem. So on a problem like this, you could multiply this out and take the antiderivative. But I just want you to recognize, if it's a calculator problem, you can much more quickly evaluate that integral in your calculator, right? So your calculator can handle evaluating a definite integral. And so we're just going to do math, the 9th option. So I have mine set to kind of the classic mode rather than the math print mode. For those of you who have the math print, it's pretty intuitive, right? It just gives you an integral. You're going to go lower limit, upper limit, function, and variable. But for those of you who don't have the newer operating system, you would do it like this. You enter the function that you want to integrate. So for me, that's going to be 3 times x minus 1 times x minus 3. And I'm going to do comma your variable, which is x, comma your lower bound, which is 0, comma your upper bound, which is 5 in this case. And hit enter. And then remember, I need to multiply by the 1/5, so times a 5th. All right, so my velocity is equal to 4. All right, so I want to know when now. Let me pull back up my slide here. So this is my average velocity. So I want to know now at what t is v of t equal to 4. And so again, we'll solve that in the calculator. I'm going to plug v of t into y1. I'll plug 4 into y2. And then I'll use my calculator to find where they intersect. So my v of t is 3 times x minus 1 times x minus 2. No, x minus 3, sorry. And then my average value is 4. I'm just going to do a zoom 6. Oh, I have a bunch of stuff up here. Turn off that stat plot. All right, so there's my 10 by 10 window. Wherever those intersect, that's the value of t that I'm looking for, where my function attains its average value over that interval. So I really only need to see window. My x window needs to be from 0 to 5 because those are the times that they want us to be focused on. So you can see it does attain its average value twice, right, on that interval. And so if I go second trace, I want to calculate an intersect, so 5. Let's find the left one first. All right, so our answer is at time t equals 0.472. And then there's one more. We'll do this one more time. Oh, sorry guys, you're not seeing my calculator online. So I just graphed my velocity and I graphed my average velocity, which was y equals 4. Anytime you have two different intersections that you're trying to find on the same screen, when it asks you for the first curve, just get closer to the other one that you're trying to find. There we go. So in 3.528. All right, so this function had an average velocity of 4. They don't give us units, which is why I'm not putting units here. It has an average velocity of 4. It reaches its average velocity at times t equals 0.472 and at time t equals 3.528.